All right, so after we introduce the linear transformer, let's talk about something called the reflected impedance. So here is a linear transformer, a typical linear transformer. And you can see here A, B, C, D. Within this border, this box, this is the transformer itself. Okay, the transformer have its own resistance. It have, of course, inductance, and you have a dots to show the polarity. And outside of that, this side, left-hand side, is the source. You're going to connect a source to the transformer, and you want to connect a load to the transformer as well. Okay, and the left-hand side is called a primary side, and right-hand side called a secondary side. Okay, the source itself, including a voltage source and the source impedance. Okay, the load is just a load. It can be anything with a pure resistive or inductive or capacitive. So it's a Z. All right. So the whole idea here is by doing a lot of a derivative, we want that, well, simplified or convert this linear transformer to this equivalent circuit. So we just reflect everything on the secondary side and represent it by the ZR, reflected impedance. Okay, that's the whole idea for this videos. The shortcuts, if you don't want to know the detail, the shortcut is ZR gonna equals to, we have equation here, ZR equals to omega, that's the impedance, that's the frequency square, M square is the mutual inductance. We're gonna talk about how to calculate that as well. Z22, which is the every impedance here, R2, L2, and ZL. Okay, that's our Z22, and that's the magnitude of Z22 square multiplied with the complex conjugate of Z22. So if you don't want to know the details, you can stop here, and this equation also will be given in the equation list. You just need to know how to plug in numbers to use this one. We're going to show an example in the next video as well. Okay, so if you still want to know how it's come from, let's quickly go through that. Okay, it's also a good practice for the induced and self-induction voltage, like the mesh methods we did in the previous video. So first, for mesh 1, for the left-hand side, the current go this way. Okay, from left-hand side to right-hand side. So you can see that it's go around, and this Vs is a voltage rise. So it's on one side of the equation. And then this is Zs, R1, L1. These all impedance. So it's follow in the convention rule that current flow as voltage drop. So these are voltage drop. So we can combine all this impedance Ds, R1, J omega L, multiply with I1. And this particular red voltage source is caused by I2. I2 is leaving the dots. So this is the dot convention. It's not passive sign. Okay, so this I2 leaving this dot, so this dot get a negative sign. So the current flow into the negative sign, out from positive sign as voltage rise. You can write this one together in the left-hand side of the equation with the Vs, or you can put a negative sign here. Okay, so that's the first equation for left-hand side. Right-hand side, you can see this one go through like this. So it's voltage rise for the red voltage source, because I1 is going to the dots, so this dot's got a positive sign. Okay, so this one is voltage rise, J omega M I1, because this caused by I1 for this red one, and then drop. Okay, 3 drop. We can combine this all together, R2, J omega L2, ZL, most importantly multiply with the current I2. Okay, equal to 0 because there's no external source for this side. Okay, so we can convert, or we can lump sum of those impedance. For example, these three impedance, we can put them together. That's exactly the same one, and give a name called Z11. So this is Z11. This 3 is Z11. Okay, and we can give a name for these three called Z22. Okay, which is just this impedance. All right, so this equation can be simplified as Vs equals to Z11 I1 minus J omega M I2, and equals to 0 equals to negative J omega M I1 and plus a Z22 I2. Okay, assume we already know the all the other parameters, then I1, I2 will be the only two unknown, two equation. We can solve that. Okay, you can do the practice yourself, but if you solve for I1, I2, you will get these solution. I1 in terms of Z22, Z11, omega, and M. Okay, and Vs. So in terms of all the other parameters. Okay. All right, so I2 equals to this, and you compare with this one, you can also see that I2 also equals to J omega M over Z22 I1. Okay, they are pretty similar except there is a Z22 there. Okay, now next part we want to calculate something called internal impedance. So let me shrink this a little bit. So the internal impedance, Z internal, is actually the voltage here. Let me give a color here. So this is the Vs. So if we use Vs, okay, Vs divided by I1, then we got this internal impedance. Okay, that's everything. If you have I and look from here, so everything from this point, it's called Z internal. So this one is Vs over I1, and you know that we already have a Vs here. So if we actually move terms in this one, okay, so because these are two are equal, so you can find that Vs over I1, you divided by I1 here and divide the whole thing to the other side, you got this one. Okay, and because there are two terms on the top, so this Z11, Z22 divided by Z22 becomes Z11 itself. Okay, and I need to probably shrink this a little bit further. Then the impedance at the terminal of the source, which is VAB. Okay, so if we look further down here, okay, so if we look at a VAB, then this ZAB equals to Z impedance, the internal, so which is the red one, minus ZS. Okay, so you can see that this was the so the total is internal. You can see that this is ZS plus a lot of stuff, and everything here is Z internal. Okay, so internal minus that one is this big blocks. Okay, this big blocks including R1, L1, and ZR, the reflect bits. Okay, so then we got this Z11. If we use Z internal, is this one minus ZS. Okay, and Z internal is everything here, and ZS is this one. So ZAB, so the ZAB is equals to Z11 minus ZS. So if you remember that Z11 actually including a ZS here, so if we cancel that, is what left is this one's R1 plus J omega L. Okay, so if you look at here is R1 J omega L is already included. So in the red box is something we call ZR, the reflected impedance. All right, so if you can see here, ZR has been copied down. So this red box has been copied down here. Okay, we can write in another form. So this is Z22, right? So there are several different ways you can write that. So ZR actually equals to omega square m square over Z22. That's it, because you can see here, this actually just Z22, right? You can also move it around like this. So it's Z22 magnitude square multiplied with Z22 complex conjugate. Okay, so the Z22 can be A plus JB form, is complex form, and this conjugate is just A minus JB. All right, so this is the reflected impedance. What we just did is to derive the equation for ZR, the reflected impedance. So we want to convert this linear transformer to an equivalent impedance, the equivalent circuit that only have one side of the transformer. Okay, we just reflect all the secondary side as this impedance. Okay, we're going to see example in the next video.